Let's take a look at this function. This is something that will come up in our study of mechanical and electrical systems. We've got a trig function here, a sine, which causes some oscillation, but it's multiplied by a decaying exponential function. So what we have is oscillation which will be dying out as time goes on. The initial amplitude is 7.1, but of course this exponential is part of the amplitude, so the amplitude will be decreasing. Now, when we go to take the derivative of this, what makes this function a little unusual compared to what we have been doing is it's actually the product of two functions. We have an exponential function here and a trig function here. So to do the derivative of something like that, we need to use our product rule. And here's the formula sheet showing the product rule. And the product rule tells us if we're multiplying, if we have the product of two functions, u and v are functions of some other variable, and we want to do the derivative of the product, that's the first times derivative of the second plus the second times the derivative of the first. Here's the Leibniz version. We can see that the independent variable in this case would be x. And again, the derivative of u times v is the first guy, u, times the derivative of the second, which is v, plus the second, which is v, times the derivative of the first. Now, of course, you can switch these two larger parts because we have a plus sign right there. So let's go ahead and apply the product rule. When doing that, in this case, it's convenient to actually think of the 7.1 as part of the first function. We could actually keep it out and apply the product rule to this part and then distribute the 7.1 in, but it's usually easier to just make it be part of this first guy. So when we go to take the derivative, y prime, we have the first, so 7.1 e to the minus 0.2t, times the derivative of the second, which I'm just going to indicate for now. I'm not going to actually take that derivative. So I'll indicate it with a prime like this, plus the second, sine of 3.5t, times the derivative of the first. So I have 7.1 e to the minus 0.2t. Oops, it's not a z, it's a 2. And we want the derivative of that. So coming over here then, this part stays the same. We still have our 7.1 e to the minus 0.2t. The derivative of sine is cosine, so we have cosine of 3.5t. Remember the argument, this part stays the same. But we do the derivative of the 3.5t and multiply the result on, so that's an extra factor of 3.5 here. Coming over here, the sine part stays the same. And the derivative of this portion, let's see, let's just do it like this. Let's leave that constant, 7.1, because it's a multiplied constant. We have e to the minus 0.2t, our exponential doesn't change. But then we have to multiply by the derivative of this exponent, which gives us a negative 0.2 factor. Okay, the derivative of negative 0.02t is just negative 0.02. So at this point we're actually done taking the derivative, but we need to tidy up a bit. We need to take each term. There's two terms here. There's this one and this one. And we want to put them in the form we had originally, constant, exponential, trig function. So we'd multiply these two constants together, which I've done ahead of time. The result of that is 24.85. So that takes care of this and this. It's good to keep track of everything, make sure you know where it goes. So those two multiply to give us that. Then we have our exponential, e to the minus 0.2t. And we have our trig function, cosine of 3.5t. Going over to this part, we're going to end up multiplying this 7.1 times the negative 0.2. So we're going to get a negative constant. So this becomes a minus sign. 0.2 times 7.1 is 1.42. And then, so that takes care of these two. Then we have our exponential, e to the minus 0.2t. And we have our sine of 3.5t. And that is our final derivative. You could, if you wanted, we could factor out an e to the minus 0.2t, but oftentimes we don't benefit a whole lot by doing that. So let's leave it at that. Now let's have you try one. The one I want to use is this. Let's use how about x? We'll make x be our dependent variable, and we'll say x equals 3.8 t e to the minus 0.5 t. And again, this is another sort of function that comes up on a fairly regular basis in some of what we'll be doing. So I'd like you to take the derivative of this. You can go ahead and hit pause, and when you're done, hit play again, and we'll see how the solution goes. Okay, so we're back to see how this finishes up. Let's use the Leibniz notation this time. So dx dt, t is the independent variable, x is the dependent variable. And again, I'll think of this as the first, so I have 3.8 t times the derivative of e to the minus 0.5 t plus e to the minus 0.5 t times the derivative of 3.8 t. Alright, so on this part here, when we do the derivative, we're still going to have an e to the minus 0.5 t, but we're also going to have a factor of negative 0.5 or negative 1/2 multiplied on. So we'll be taking negative 1/2 times 3.8, so that's going to be a negative, and half of 3.8 is 1.9. Okay, so again, this 1.9 is coming from a negative 0.5 we'll get from the chain rule here times that 3.8. Over here, the derivative of 3.8t is just 3.8, so this is going to be plus 3.8 e to the minus 0.5t. And that, in fact, is our final answer. If we wanted, again, we could factor out an exponential. It looks like I lost a t right here. Sorry about that. So we've got a t right in that spot there. If we were to factor out the exponential, the e, we'd have negative 1.9t plus 3.8 e to the minus 0.5t. Either of these is acceptable. And let's see, there's one other thing I'd like to look at concerning second derivatives. We'll leave that for the next video, next and last.